Okay, so we have 5 people here online. So let's get started. So last time we talked about the properties of Fourier series. Okay, and let's go over them again. So given two periodic continuous time signals x, t, y, t, and assuming that their corresponding Fourier series spectrum is given by AK and BK, then we have the following properties. The first one is linearity, which is very intuitive. Now the second one is a time shifting property, which says that if the signal is shifted in time, then the corresponding spectrum AK will be modulated by a complex exponential. And this complex exponential, when we multiply AK by this complex exponential, we are essentially modifying the phase component of the spectrum. So that is to say, a time shift in the time domain will cause a phase shift in the frequency domain, in the spectrum domain. And I think we will prove this later when we talk about Fourier transform. But it is essentially a change of variable in the integration. And then if we multiply the signals together, then the spectrum of this signal is given by kind of discrete convolution between the spectrum, between their spectrums. And then we have this conjugation property. Well, for any periodic signal xt with AK, spectrum AK, the conjugate, now consider the conjugate of the signal, x conjugate t. The spectrum of this signal is given by taking the original spectrum, and then we do a reversal, do a time reversal, a negative k, and then taking the conjugate. And in particular, if xt is real valued, which means xt equals to its conjugate, right? That is the definition of real valued signal. So if xt is real valued, then these two signals are equal. So are their corresponding spectrums. So in that case, AK equals to A negative K to the conjugate, which means A negative K is the conjugate of AK. So we have this conjugate symmetry. And if we do a time reversal on the signal, the corresponding spectrum will also be reversed. So this is also intuitive. And we have two more properties. One is about differentiation, the other is integration. So if we take derivative of the signal, then the spectrum is modified by multiplying by a constant, j, k, omega naught. Okay. And instead, if we do integration, then the spectrum is divided by this constant. So from these two, we can see that if we do differentiation and the integration in the time domain, and notice that these two are usually computation intensive, right? In general, taking derivative or taking integration. However, if we deal with these two operators in the frequency domain, they are very simple. It's basically multiplying the spectrum by some complex numbers. So multiplication is always simpler. And today we're going to talk about one important theorem, the Parseval's theorem, which basically says that the energy of a signal should be invariant to the domain that we are considering. So if we calculate the energy of the signal in the time domain, that should be equivalent to the energy of signal when we calculate it in the frequency domain. Okay. So this theorem corresponds to this equation. On the left-hand side, because xt is a periodic signal with period capital T. So the left-hand side is basically if you recall the definition of power. Right, so the left-hand side is the power of the signal xt over the one period. Because inside this integration collects the energy of the signal over one particular period, and then we distribute this energy over the entire period, 1 over t. So that is similar to the definition, kind of like the definition of power, but only within one period. And then on the right-hand side, we are looking at the spectrum. We are summing up the magnitude of the spectrum to the power of 2, which corresponds to, if we treat the spectrum AK as a discrete signal, because AK, the index K is a discrete index. So we can generally treat AK as a complex discrete time signal. So the right-hand side corresponds to the energy of that discrete time signal. And this signal is actually the spectrum of the periodic signal xt. So the right-hand side is essentially the total energy of the signal in the spectrum domain. And the Parseval's theorem says that these two must be equivalent. And actually, the proof of this theorem is very standard. So we can take a brief look at the proof logic. So we start from the left-hand side, and then notice that xt, the magnitude of xt to the power of 2, we have a famous equation for that. You still remember? Any complex number its magnitude to the power of 2 equals xt times its conjugate. Okay. And then because xt is a periodic continuous time signal, we know that xt has a Fourier series representation. So we plug in its Fourier series representation here. Right, so now xt is this Fourier series. Okay, so this part, the first summation, this summation is essentially xt, right? It's just the Fourier series representation. And the second summation is xt to the conjugate. So now we are taking the conjugate of the entire Fourier series representation. So, which means we need to take conjugate of these coefficients as well as these basis signals. So after conjugation, AK becomes A conjugate, and this exponential becomes their corresponding conjugate, complex exponentials. And here to differentiate these two summations, I'm using two different indexes. One, the first series uses index K, while the second one is using index N. Okay. So for the first step, we are just leveraging this equation for complex numbers, and then substitute the Fourier series representation into this xt and xt conjugate. Okay. Now we have transfer the signal into the frequency domain by using the Fourier series. So now let's look at this double summation. Now this double summation, we can combine them. We can pull this summation in the front. So we have double summation over k and n. And now we can multiply everything inside the summation. So we have ak, an conjugate, and these two exponentials, combine them gives this one. Okay, just a simple calculation. And what's next is that, so next we are just exchanging this integration, the order now between the integration and the double summation. So we put this double summation in front and evaluate the integration first. So note that this integration is evaluating over t, small t. So which means these two can be treated as constant. So the integration is basically operating on the complex exponential part only. Okay, so ak, an conjugate, both of them does not depend on the small t. And then in the previous lecture, we showed that such an integration is basically a binary indicator of k and n. We go back to the one of the lectures slides right here. Right. This integration, 1 over t integration of these two complex exponentials, they are just a binary indicator, indicating whether or not this index k equals to L. Okay, so let's remember that. And with this result, going back to here, so basically this entire integration is an indicator function of k equals to n. Therefore, if k and n, if these two index, and note that this k and n are the index in these infinite summations. If they are not equal, this integration is simply 0, right? Because it's the indicator function. So we only need to consider, well, this double summation will go over all the possible combinations of k and n. But because this last term is an indicator of k equals to n, so we only need to consider the case when k equals to n in this double summation. And that simply corresponds to the diagonal element of this double summation. So in the end, these two becomes 1. So we only need to consider when k equals to n, and which means we can just use k to represent that instead. So when k equals to n, ak, an conjugate is becoming ak conjugate. And in that case, this integration is the 1, the indicator 1. Okay, so in the end, we reduce the double summation into a single summation. And looking at this one, ak conjugate is simply ak, the magnitude of ak to the power of 2, which is the right-hand side of the equation. So here we are just utilizing the Fourier series representation of the signal. And then following some basic calculations, we can derive this Parseval theorem. And in one of the homework 5, you will need to utilize this Parseval theorem to smartly compute a summation series. We can briefly talk about that later. Okay, so this finishes the Fourier series part for continuous time signals. And correspondingly, we can define all these Fourier series for discrete time signals, for periodic discrete time signals. However, the Fourier series in the discrete case is a little bit different. So let's look at the discrete case. So we consider a discrete time signal xn, and also similarly, we consider the periodic case. So let's assume that this signal has a period capital N, which means xn equals to xn plus capital N. And then in order to represent such a periodic discrete time signal, we are going to build up a set of basis functions. But in a discrete case, it is a little bit different. So we first consider the set of complex exponential signals that are periodic with the fundamental period capital N, which is given by the following phi kn. Okay, so we are considering a signal, discrete signal with fundamental period capital N, and then to develop the corresponding Fourier basis signals, we considered all the complex exponentials, discrete complex exponential signals with period capital N, which is denoted as phi kn e to the power of j k omega naught n. Now this looks very similar to the continuous case, right? If you replace this m by a continuous index t, that is essentially the basis in the continuous time. So in this case, we know that omega n is the angular frequency, which is essentially 2 pi over capital N, small n. So this k again, this k is the index of the complex exponential basis. So phi kn denotes the case basis signal. And again, this k take all the integer values. This is the same as the continuous time case. However, the difference is that in the continuous, in the previous continuous time case, right, we have a t, we have continuous time t here instead of discrete index n. And in a discrete case, this small n can only take integer values. That actually makes the entire infinite number of basis signals reduces to a finite number of basis signals because it has a periodic structure. So since n is integer, or discrete time, because we are considering discrete time signals. Now, because this in the discrete time case, the time index n can only take integer values. That makes phi kn periodic in this following sense. So the case basis is actually coincides with the k plus any integer times capital N's basis, which means that the basis is periodic with a period capital N. So to be more specific, okay, here we are considering infinite. So following the continuous time case, right, we may want to consider all the entire set of basis signals, where k takes all the integer values, positive integers, negative integers. So it seems that we have infinitely many of these basis signals. However, it turns out that if we write them one by one, we have phi 1, phi 2, phi n plus 1, and so on. We have phi 0, phi -1. And it turns out that phi 1 equals to phi n plus 1. Phi 2 equals to phi n plus 2. Right. So we just need to consider one subset of this, because they are periodic. Phi 1 equals to phi n plus 1, phi 2 equals to phi capital N plus 2, which means that we only have a finite number of basis signals in this case. And why is this true? You can check that. We can prove this. We can consider this one. Phi k plus Rn. Now, following this equation, we just need to replace k by k plus Rn. So that gives us Ej k plus Rn times 2 pi capital N small n. And then we can decompose it into two parts. And the first part only considers the k, and then the second part involves r times n. But r times n, this capital N cancels with the denominator, so we have j r times 2 pi times n. And this is exactly phi k. This is exactly phi k. But this one is very special because this time index n can only take integer values. So n is an integer, r is an integer. So we are looking at e to the power of j some integer times 2 pi. That is a constant 1 by the Euler's formula. Right? So both n and r are integers, integer times 2 pi. So the phase part is some integer multiplied by 2 pi, which gives a constant 1. Right. So this shows that if the time index is discrete, then this basis has a periodic structure, and consequently, we only have finite number of distinguished basis signals, and the number of bases equals to the fundamental period of the signal of interest. Okay, so this is the key difference between the Fourier series for continuous time signals and the Fourier series for discrete time signals. In the continuous time domain, we need infinitely many of the basis signals. But in the discrete time domain, we only need a finite number of them, which makes sense because for discrete signals, it is simpler, right? Because they only locate on the discrete time indexes. So that should be more regular. So we only need to have a smaller number of basis signals to represent this class of signals.
I have a quick question.
Yes, let me, okay.
The numbers next to the phi's, do those represent what k would be? When you were listing out like 5, -1, 5, 0, 5, 1, 5, 2, would those numbers be k?
Okay, okay. That simply, yeah, that means we need to only consider k Okay, let me write it here. Yeah. So originally we have this k, right? The range of k is any integers, right? Can see, including both positive and negative integers. So here we have infinitely, here we have infinitely many of them. But up with this periodic structure, we only need to consider phi k n, well, k is 1, 2, up to capital N.
Okay.
We only need to consider this finite number of the bases. Yeah, because all the other bases, any of them will be equivalent to one of the bases here.
Okay, that makes sense. Thank you.
Yeah. Okay. Therefore, for discrete signal with fundamental period capital N, the set of discrete eigenfunctions, okay, this basis eigenfunctions, we only have a finite number of them. Okay, so here's this phi kn, well, k is from 0 to capital N minus 1, or you can consider 1 to capital N. They are the same because of the periodic structure. So k is between 0 and capital N minus 1. And then this means that if we consider any discrete time periodic signal, xn, then we can write xn, we can decompose xn into the following form. Xn equals to summation, it's a linear combination of all these eigen functions or basis functions. And the linear combination coefficient is ak, which is again the spectrum of this signal. But the only difference is that now we only have a finite number of these basis functions. So the k ranges from 0 to capital N minus 1. Right. Now, recall that in the continuous time case, this k ranges from negative infinity to positive infinity. So here we only need a finite number of them. And then the rest of the story is the same. We need to calculate for a given signal. We need to calculate the spectrum. So the calculation can be conducted by, again, projecting the signal onto each of the basis signals. And such a projection is defined by this summation. So it's 1 over n sum over small n. So we are considering all these basis signals, and we are projecting our signal xn onto each of them. Therefore, think about this. If we are given xn, if the signal is given, and if the fundamental period is given, capital N is given, so omega naught is also given, then we should be able to calculate this summation and then work out the spectrum. So as long as the signal xn is given and the fundamental period is given, then we can calculate the AK following this formula. The structure is exactly the same as the continuous, the formula for AK in the continuous time case, except that there we have integration, but here we only have summation because we have finite number of these bases. So we do summation instead of integration. Right, and the way you calculate this AK is, again, following the standard steps. You first, given the signal and the fundamental period, you work out the fundamental angular frequency, which is 2 pi over capital N. Okay, this one. Now you have this. Once you have that, then you plug in xn, the signal, into this formula, and then calculate this summation. And for this discrete time Fourier series, it also has similar properties as the continuous time Fourier series. So most of the properties for discrete time Fourier series are similar to those for continuous time Fourier series. However, there are a few important differences. So let's go over this one. So the first one is linearity. This is the same. If we have two discrete time signals with their Fourier series spectrum, then adding them up, this sum of signals, the corresponding spectrum is AK plus BK. Is the sum of the corresponding spectrums. And time shifting is the same. Basically, a shift in the discrete time domain will cause a phase change in the spectrum domain. Okay. And the phase change is the same thing. It's e to the negative jk. This is omega naught times n naught. And this one again is the same as the continuous time case. Multiplication in time corresponds to convolution in the spectrum domain. Conjugation, real value signal, these two are the same. So all these properties are similar to the continuous Fourier series. And time reversal, again, is the same. If we do a time reversal in time, the spectrum is also reversed. So the difference is the differentiation part. Now, recall that in continuous time case, we have a differentiation property. We have this differentiation property where we consider the derivative of this continuous time signal. But now we are looking at discrete time signal, so we don't have derivative anymore. Instead, we consider the difference as a kind of approximation of the derivative. So such a first difference signal, which means xm subtracting the previous xm minus 1. This difference signal, the corresponding Fourier series spectrum is given by this one. It's ak times such a constant, 1 minus e to the power of negative jk omega naught. So this is one of the difference, the differentiation part. And then for this discrete time Fourier series, we also have this Parseval theorem. So the energy in the time domain is preserved in the frequency domain. So this formula is exactly the same as the continuous time Parseval theorem. But the only difference is that in the continuous time, we do integration here because we are dealing with continuous time signals. But in the discrete time, we calculate this, the left-hand side, over one period of the signal. But now, since it is discrete time, so we do summation instead of integration. And on the right-hand side, it's basically summing up, collecting all the energies in the frequency domain. But in the discrete time case, we only have a finite number of basis eigenfunctions. So the summation on the right-hand side only involves this a finite number of terms. So if you compare this with the continuous time Parseval theorem, right, because in the continuous time, the spectrum has infinitely many, this AK, the index for K, has infinitely many cases. So we have to sum up K from negative infinity to positive infinity. So this is the only difference. But the key idea is the same, because in this case, the right-hand side still can be interpreted as the total energy in the frequency domain. Okay, so now we have one exercise, which is actually very related to the sampling lecture that we will learn in the following lectures. So given rewrite the following periodic signal into Fourier series, where T0 is the fundamental period. Now, I will give you 3 minutes to work on this, but just to give you some understanding. First of all, this is a continuous time signal, right? It's xt. So you need to apply the continuous time Fourier series formula to calculate the spectrum. And the signal looks like it's a summation of shifted impulse signals. Now K so it's a periodic impulse. Right? If you let K equals to 0, we get delta T. So this one, K equals to 0. If you let K equals to 1, we have delta T minus T capital T naught. So this is 1, this is 2. And we are summing up infinitely many of these impulses. So they are located with a constant distance to each other. So let me write this down on the screen. And now go back to the continuous time Fourier series. Now I give you 5 minutes. Calculate the AK, the spectrum of this signal, by leveraging this formula. Okay, 5 minutes. Yeah, a hint is that you plug in xt into that formula, right? You have integration and followed by infinite summation. You can consider switch their order, but do the integration part first. Okay, so let's take a look at this one. So let's follow the formula. We're integrating over one period. So I can take negative t naught over 2, t naught over 2, which only includes one impulse centered at the original point. So with that, so I have summation, because I used the k here, so I'm going to use a different notation for the index. So this is xt. This is xt. Xt e negative j k t. And then we said that we can consider switching the integration with the summation. So we ended up with this one. So what is the next step? What is the next step? How to calculate this integration? Change of variable. If we do that, we can do a change of variable. And then we will have delta t, for example, and this one t becomes t minus something or t plus something. But we still have this impulse. How do we deal with this impulse in this integration? So we're integrating the impulse times a function. We have one trick for that.
Can we change the limits?
Change limits. Yeah, I think you mentioned the right. So we have a formula in the previous lectures which says that the property of the impulse, right? So it's delta t minus anything so this impulse times n in ft, we can just replace ft by constant value f evaluated at this time shift capital T. So here our time shift is n times t naught, and this can be regarded as this function ft. Therefore, this becomes well, this becomes delta This one is the same, and this one is j, k, omega naught, and replacing t by this shift. By the shift. And this is a constant because it doesn't depend on t, so we can pull it out. So this becomes, and inside we are integrating over this impulse signal. However, this integration is restricted between between one period. So you can see that if this n, suppose n is 0, then this delta t. So we are looking at this impulse, which is within this period. But if n is other than 0, like either 1 or -1, so we are shifting the impulse to the right or to the left by t naught. And then that will be outside the period that we consider. So it looks like the only case that this integration gives a non-zero result would be n equals to 0. So which is 1/0, or 1 over t naught. This n is from -infinity to +infinity. Only n equals to 0. Oh. But only n equals to 0 will give this integration constant value, and this is just 1 because it's integrated over the impulse. By definition, is 1. If n is other than 0, then this impulse will be shifted outside this interval. Then the integration is only over a 0. Okay, so in the end, we have this very simple formula: 1/t e -j k. Now, what is omega naught? Omega naught is 2 pi over capital T naught. So we cancel that. It's 2 pi n. Oh, sorry, this n is 0. I forgot. Yeah, I should have. Okay, only n equals to 0 makes sense. So we should plug in n equals to 0, which makes this 0. Yeah, this should be 0. Now 0, this basically gives us 1. E to the power of 0, that gives us 1. So what do we get? AK equals to constant 1/0. Therefore, the spectrum of this periodic impulse signal is the spectrum is just a constant 1/T0. Okay, so the spectrum is constant. We draw K, AK, then it's a constant.
When you're choosing your limits of integration, could you do 0 to t instead of -t/2 to t/2?
Yeah, that's a great question. Yes, we can do that. So just a comment here. If we do that, so then we need to be a little bit careful, right? So if you choose 0 to t naught, then this one, okay, AK is just 1 over t naught. Let's say 0 to t naught. So you should actually, because when you consider 0 to t naught, you actually have two arrows at the end of this interval. So you need to consider either excluding 0 or excluding t naught. So for example, I can consider t plus to t naught plus, which is basically 0 to t naught.
In that case,
either one of them.
in that case, would it be a 2 over t naught?
I mean, the final result, we can check that. We can check that. Let's. Can we just follow this one if we do? Okay. If we do t0 to t naught, let's say, let me exclude 0. Okay. Because in general, you see that every period we only have one impulse. Right? If you consider negative t over 2 to t over 2, we only have one impulse. So if you consider 0 to t naught, make sure you only consider one part of it. So here I'm excluding 0. Okay, this one, now xt is that summation delta t minus nt. Okay. And then we do the same thing. We have 1 over t naught sum over n and integrating and this one becomes e negative j k omega naught again and capital T naught dt. But now, since we are taking integration between 0 and t naught, so the only case, so the only arrow that lies into this integration is this one, right? Well, because we exclude the 0 one, so this one does not exist. So the only one we include in this interval is this arrow. And this impulse corresponds to when n equals to 1. It is delta t minus capital T naught. Therefore, we only need to consider when n in this entire summation when n equals to 1. So that gives us 1 over T naught. And the entire summation, we only consider one of them. So it's integration. Now when n equals to 1, we have t minus capital T naught. And it's e negative j k omega naught t naught dt. Right, because n now equals to 1. And this is a constant, doesn't depend on t. So this integration over delta is 1. So the result is 1 over t naught e negative j k omega naught t naught. Which is the same because this is 1. Right. Because it's tricky, omega naught here is 2 pi over t naught. And these two cancel out. So you have e to the power of negative jk times 2 pi. The face part is integer times 2 pi. Again, it's the integer times 2 pi. So this makes this entire exponential constant 1. Okay. And you can see that and then we have the same result. So no matter which interval, which period you choose, and this is because of the periodical structure of this complex exponential, we always get the same result. Yes.
So when you're studying the bounds of these integrations, do you always have one and be exclusive and the other inclusive?
Yes. It's actually a little bit tricky. If I consider negative t over 2 to t over 2, then from the picture, I can see that it includes the impulse in the middle, right? And at the ending point, there's nothing there. So I don't really need to care about whether to close the interval on these ending points. But when you consider 0 to t naught, then it looks like you will touch 2 arrows, but you should only consider 1 because the period is just 1. So the impulse only repeats for every t naught seconds. So make sure you always make it half open and half closed. Okay, so in the end, right, no matter which period you consider, following this formula, now in this calculation we need to leverage the property of the impulse functions, right? We are leveraging the property. So first of all, we exchange the order of integration, the summation, and then inside the integration we can deal with this integration of the impulse by leveraging the properties of the impulse. And after that, we need to consider, we can see that this integration of the impulse only take non-zero values for certain impulse because the integration, so here the integration only is only over one specific period. However, we are looking at infinitely many impulses. So only one impulse will be located in that period. So can only consider that one, we can get the final result. And turns out to be a very simple real value constant. This is not, first of all, to answer the first question, is this a discrete case? No, we are looking at continuous time signal, right? We have xt is a continuous time signal defined as, because we know the impulse signal, delta t, right? The t is a continuous time variable, so delta t is continuous time signal. We are summing up infinitely many of the impulses, which are periodically located over the time interval. So xt is a continuous time signal. It looks like discrete, but here the t is continuous time. Remember that it is not xn. So this integration, to answer your second question, right? This integration, this formula for calculating the spectrum, we need to integrate in over any one period. So we just consider, we have considered two cases. The first case is to consider the period negative t over 2 to t over 2. Because it's the fundamental period is t naught, so any interval that spans a length of t naught would be a period. So this is one case that you can consider. Now we also consider the second case where we consider 0 to t naught. Okay. You can also do t naught to 2 times t naught, and you will get the same result. So no matter which period you consider, you will always get the same result. Okay, and this signal is particularly important because, well, we can do sampling by using this signal. If you have any continuous time signal, you multiply that signal with this, looks like a comb. With this comb signal, then we are basically sampling the continuous time signal at these discrete time points. Right? So it's so we will later in the sampling lecture 7 or lecture 8, we will leverage this signal to discuss the sampling issues. You can see that if we use this sampling signal, the spectrum is very simple, it's just a constant. So if we do Fourier analysis on this signal, so basically dealing with signal in the Fourier domain is much more convenient than in the time domain. Because in the time domain, you have infinitely many of impulses to deal with. Okay, so I think this finishes this lecture 5, where we talk about Fourier series for representing periodic signals. Okay, remember the Fourier series can only represent periodic, either continuous time or discrete time signals. And briefly look at homework 5, see. Okay, quick comments on these problems. First one, given this periodic signal, fundamental frequency is given, which is by looking at the GCD of these angular frequencies. Find Fourier series coefficient AK of xt. Well, this is already in the sinusoidal form, so you just leverage the inverse Euler's formula. Okay, that's simpler. B is given 3 signals in the Fourier series form, 1, 2, 3. Which of the 3 signals are real valued? Okay, so then you need to consider the properties of Fourier series of real value signals. Go back to the list of properties. We have one property on the spectrum of real value signals. Problem 2, given xt in the figure below is a periodic rectangle signal. Find the Fourier series for xt. Okay, just do the calculations following the formula. So this part is standard. Problem 3, let xt be a continuous time periodic signal with period t equals to 3 given by this one. So you can sketch this signal between -1 and 1. It's a constant, so it's a flat curve. Between 1 and 1.5 is 0. So it is a rectangle signal. And then this is only one period. You repeat this period periodically. Part A, sketch this signal, very simple. Part B, find the fundamental frequency and the Fourier series coefficient AK of this signal. You can use this result to get answers for the remaining part. Okay, part B is also standard. Basically, once you sketch the signal, it is something, maybe something similar to this one. And then you follow the formula, do the calculations, you can get AK and omega naught. So this is part B. Part C is to let xbt be the continuous signal given by this one, which is a little bit than xt, right? Because they have different values in these different intervals. Find the Fourier series coefficient bk of this signal. Well, you can do that in the standard way by leveraging the formula of AK, but here I want you to follow the hint of part B. You can use the result of part B to get the answers for C and D. Okay, the key is to build a connection between xt, between this signal and this signal. Okay, maybe through some simple transformations, scaling, time shifting, time scaling, you can establish a relation between xt and xbt, and then leveraging once you know from part B, you know the spectrum of xt, and then you can leverage some properties of Fourier series to directly obtain the spectrum of part C. So that is the key idea. Part D is the same thing. We have another signal xct. Again, you can follow the standard formula for AK to calculate the Fourier series. But here you can try to build a relation between xt and xct. So by through time scaling, I think we need to have time scaling here because the range now is scaled by expanded by a factor of 2. So you need to consider time scaling. And after that, you can leverage the properties of Fourier series to derive this. So once you have part B, you should be able to get C and D very conveniently. Now the last one is a little bit tricky. Part E, what is the limit of the infinite sum of this signal, which looks completely disconnected from the previous problems. But it looks like a mathematical problem. The hint is to connect this series with the Parseval's theorem. Now, if you do this is Parseval's theorem. Now, if you do the calculations correctly, I think you will find that if you look at Parseval's theorem, this summation series looks like the right-hand side, right? The sum of squares. Now, if you do part A, B, C, D correctly, you will find that for one of the signals, xt, either xt or xb, xct, one of them, for one of them, their corresponding spectrum AK will be equal to this value. And then by applying Parseval's theorem to that specific signal, you can conclude that, okay, this summation in the energy collected in the frequency domain equals to the energy that I collect in the time domain. Therefore, by Parseval's theorem, you can say that this summation series equals to the integration of that specific signal in the time domain over one period. So instead of directly calculating this infinite summation series, you can calculate this integration in the time domain. And that is very simple because all these signals in the time domain, they have very simple analytical expressions. It's very simple to do the integration. And then that's how you can get the result for this one. Okay. So you can use Parseval's theorem to calculate this infinite sum. I think problem 4 is that we are given an LTI system with a frequency response given by this one, and then we are inputting a periodic signal, determine the output. So the idea is that since we are given the frequency response, so we know that is this slide, we are given this frequency response. So the idea is to first decompose the input into these eigenfunctions, eigensignals, by following the Fourier series, right? And then because it's LTI, so the corresponding output is basically given by this one. It's all the Fourier series, every Fourier series, eigenfunction in the Fourier series will be passed into the system, and then we sum them up. Now, for each of these eigenfunctions, the corresponding response is given by this frequency response. So again, here you need to do a Fourier series expansion first, and then leverage the LTI property of the system. Okay. Yeah, so I think these are not, most of the problems are not that difficult, but for problem 3, make sure you utilize the properties of Fourier series to simplify, to avoid calculations. CDE can all of them can be done without intensive calculations. That is the main idea. Okay, so do you have any questions? Okay, if there's no questions, I think we can stop early today, and I will be in the office hours 5 minutes later. Okay, I will see you guys next Tuesday.